Greetings, friends. Welcome to week 5, and this will be our the start of our 5th week. This is week 5, class number 1. So we are here, and it is time to start the. You've got 4 solid weeks full of having reviewed for the final. So I guess we'll just keep doing that. A couple of things before we get going. The usual PLC 5 is up, and that's for Friday. We are going to go through, so this is on stuff that we may end up barely starting today, but we will be talking about in depth on Wednesday and Thursday. So we'll have 2 classes on this. Hopefully that should be able to get you in good stead for that. If not, we'll figure things out. Remember that homework 2 is up. And the quiz is going to be here on Thursday of this week. So a couple extra days to turn in homework. And remember, quiz is on the day of the due date for the homework. And I have over the weekend graded the first 2 quizzes. I believe I did both of them, and I think I put them out, like I sent your grades out. And there were a number of late quizzes. I just want to remind you that's not gonna work. So partially, well, we're going to have the quizzes on the full day. I give you the full day to do it. And if it's not done, then I'm sorry, it's not going to work. So try to keep up and stay on point with those as best you can. Also, in terms of late assignments, I encourage you to review the syllabus. There are 2 free late assignments that I give you. You pick a homework, or 2 homeworks, or 1 lab, or 2 labs, whatever. It's a combination of homeworks and labs. You get 2 free lates, but that doesn't mean that you can just turn them in whenever you want. It's got to be by the next day. And if it's not in by then it's half off. And then if it's not in by the following day, then I'm not going to accept it. So please try to stay up to date with your work. I know that's very difficult in an online class, but in order to keep things moving, I have to be able to receive work, try to grade it as best I can, and get it back to you. So if work is still coming in and I'm still in the middle of grading other stuff, then I don't have the bandwidth to be able to deal with late assignments whenever. So I have to have this policy in place. And I'm trying to give you some leeway, so be aware that there are 2 free lates, and that is only until the next day. All right. So hopefully lab 3 went well with lenses. We had a little bit of fun looking at the lens images and trying to figure out the lens curvatures and the focal points and things like that. So hopefully you enjoyed that. We will be into interference on Friday of this week. And speaking of interference, we're going to go through thin film interference today, and I think that's pretty much going to wrap up what we have to say on interference and general wave characteristics in general, meaning that the polarization and the radiation pressure are other things that we went through. And we're going to move away from talking about wave characteristics and double slit interference, and we're going to go into something else. Probably, like I said, tomorrow we'll spend the bulk of tomorrow and Thursday talking about that. So just by way of also other reminders, the first celebration is going to be coming up probably in about 2 weeks, okay? And it's going to be on everything to do with optics. We will have finished optics the week before, so you'll have the entire unit on optics, and we'll stop, and then we'll probably do a quick review there, and then we're going to move into thermodynamics, and then the celebration on optics happens as we have already started the thermo unit. Okay, so this is about a 2-week notice. All right. We can talk more about the celebration mechanics. In other words, how is it getting distributed and what's happening? It's basically like a quiz, like one of the homework quizzes, but we'll go into more detail as the time approaches. So for this week, PLC 5 and homework 2 and homework 2's quiz, and that's all interference stuff on the homework 2 stuff and polarization. Okay, so with that being said, I want to talk about thin films and how we find and assess what interference is happening when we have light that bounces off a boundary between two materials and then while some of it bounces off, some of it goes in, I'm considering transparent material, and bounces off a lower boundary and comes out, and then those two waves are interfering with one another. And the picture, if you remember, looks something like this, where I have a thin layer of something, and I used the example of water on top of glass, like a very thin layer of water on top of glass. I also mentioned this could be the thickness of a soap bubble. When you blow soap bubbles, there's going to be air on this side, and this is a thin water boundary between the two pieces of air. So anything that's thin enough where light can go, and remember, we're doing this always at normal incidence, okay, so that we're not going to consider refractive angles in our path length differences. This is going to be normal incidence. So, but in order to be able to see the waves, we have to draw them not at normal incidence. So here comes incident light here, like so. And when I draw it that way, you just have to imagine that it's instead of an angle, it's just coming straight down and then bouncing straight back up, because there would be no refraction in this case, right? Your sine would be your sine of the angle measured to the normal would be 0. So we have no refraction here. We're going to get one bounce from the top surface here, which I called this reflected number 1. This is the R1 wave, and we wanted to assess the interference of that with the wave that has entered the material, bounced off the lower boundary, and then come out like this, and I called that reflected wave R2. So we are trying to assess the interference between these two. Okay, so I mentioned that there are 3 interferences going on. All 3 of the ones that we've talked about are here all together. So let's just review quickly what is going on here. Number 1, at both of these reflections, we're going to have a phase shift, or let me put it this way, we have the possibility of getting a phase shift. So we have to check for the reflection phase shift here. Okay, we're going to get the reflection phase shift happening at both of those, or at least we need to check it. We have a path length difference because wave R2 has gone in and out of the material, and remember this is at normal incidence, so if we call this material thickness T, then we have a path length difference of 2T for R2 above R1. And then lastly, because wave R2 is in a medium with an index, the wavelength will be shortened, and also we have the wavelength reduction inside the thin film itself. So if I call this material 1, 2, and 3, then this is going to be N2, or really I should have called it 0, 1, and 2. Well, this is the lambda. Okay, I guess I'm going to have to recall this lambda 1, but that's, you know what? I'm not going to do that. I'm going to leave it lambda naught because that's what we've called it. I'm going to change this. Okay, we're going to do this, and I'm going to change that. Okay, so this is going to be 1, and this will be 0, 1, and 2. Okay, so that lambda naught, which is the wavelength typically in air. So for example, if my naught material here is air, then I'm going to take that, and I'm going to reduce the wavelength when it's in material 1 by the index of material 1. We have all three of these going. We did kind of leave off last time talking about how to assess all of these at the same time and put the interference conditions on. So let's go through and I guess let's just do an example. Let's just do some examples today. We know that, I'll just write the interference conditions here, but we know that from the double slit experiment, we know that constructive interference is going to happen when these two waves, R1 and R2, are coming out with an integer difference in the wavelengths. Okay, we know there's going to be destruction, complete destruction between R1 and R2 when they come out with an integer plus a half difference in times wavelength. Okay, so when we put all of this together, we have constructive. Okay, now the issue here is when thinking about the double slit and the constructive and destructive interference conditions, right? We can think about the path length difference as supplying some bit of phase shift for the waves, but we also have to remember there's going to be a phase shift due to the reflection. Okay, so when we think about construction and we say, oh, it has to be an integer number of wavelengths, what that means is ultimately we need to have them swimming in phase like this. Okay, and the way you get that is having a integer number of wavelengths in the path length difference. But now we also have to assess the reflection phase shift. So I kind of misspoke there. I jumped the gun a little bit on that one. So really what we want is constructive to know that they're in phase so that they've emerged. I probably should not, in fact, I definitely should not have said an integer number of wavelengths. I should have said that their crests are still matching. Okay. So I caught myself there, actually, barely. But nonetheless, all three of these things together have to line up the waves in order to get construction. So that means if I have a half wavelength difference in the path length difference, that's going to get put aside. That's going to get balanced, say, by the half wavelength that might occur here in the reflection phase shift. All right. So constructive happens when you get the waves going like this. Destructive happens when you get the waves going like this. And unlike double slit experiment, the conditions actually you have to let them determine themselves, or you have to be flexible enough to say, okay, here's what we need to have happen. All right. So constructive happens when you have this. And destructive happens when you have this. Destructive happens when you have this. All right. And how you get there is through the combination of all three of these. So let's just do an example and kind of maybe you can see it in action and that'll help out a little bit. Let's do this. I'm going to go ahead and keep this picture here. And let's take a look at a situation in which I have a light incident here, and I'm observing a constructive pattern and a destructive. I'm observing the interference pattern. okay? And I'm asking, okay, what kind of thickness must this thin film have if I'm observing this particular construction, destruction of wavelengths, okay? All right, so let's take a look. All right, so we have a thin film, and let's see here. I wanted to just take a look and see what we have here. All right, so I've got a thin film. I've got some liquid, right? Some thin film of, say, I just said acetone, and it's got a slightly lower index than glass, and slightly lower than water as well. Thin film of acetone on top of a glass plate. Top of a glass plate whose N is 1.5. All right, now I'm going to shine a couple of different wavelengths down onto this, okay? As always, completely normal incidence. All right, now I'm going to see, when I do that, I see destruction of a wavelength of 600 nanometers. Okay, and now I get full construction of a wavelength of 700 nanometers. And so what we want to do is find what thickness of the acetone is creating this situation. Okay. So you can imagine that I'm looking at white light incident onto this thin film of acetone here with glass underneath. And in the white light, there are these two wavelengths, 600 and 700. They're both, this one's kind of orangey, this one's more deeper red. And I'm noticing that this orange is gone. It's not there. So it's kind of like when you look at oil on top of a water puddle or something like that, and you see that kind of swirly rainbow. You'll notice that from some angles or from some positions where you look at it, because the thickness will typically be slightly varying, you'll see that there's more of a green over here, and you look over here, there's more of a reds and yellows over there. So what you're noticing is that in this case, suppose I had a way to measure, but I'm not noticing the absence of that wavelength, but I'm noticing a very bright one of those. Okay, so my question is, what thickness creates that interference pattern? Okay, so let's take a look at trying to assess the interference here. Let's go here. Okay. All right, so if I have destruction of the 600 nanometer wavelength, all right, I know that when I'm going from air, in which N is equal to 1, to acetone, which is 1.25, into glass, which is 1.5, then I can assess these reflection phase shifts right away and say, I know I'm going to get a plus half a wavelength here, and I'm going to get a plus a half wavelength here, because as you go up in the index, the phase shift is plus a half a wavelength. So that's the same as pi, that's the same as 180. So what I typically do is here, I just remind myself of that by putting plus pi on any one of these waves, which is going to be reflected off a boundary in which it's going to experience that wave, that phase shift. it also happens to that one. So I'm going to put a plus pi on that one as well. Okay. Now, the way I think of this is I look at those and I say, okay, so the reflection phase shift is really causing nothing to happen, right? It's causing nothing untowards. I'm going to have no difference introduced by the phase shifts due to reflection. I am therefore going to have most of the effects due to path length difference and wavelength reduction. And furthermore, if I say that I want construction, then I can use the double slit construction of integer wavelengths because these two things are not contributing any extra phase shift, right? They're both out of phase with what they were, but they're both equally out of phase with what they were, so these don't do anything. Okay, so for the destruction of the 600, what we'll find I'm just going to call that lambda 6. I'll call the 600s lambda 6 and the 700s lambda 7. So instead of lambda 1 and 2. I don't know, maybe that's stupid. But anyways, destruction of lambda 6 is going to come about because I'm going to call this m of the 6 plus a half times lambda 6 is equal to, and remember that lambda 6 usually would have an n underneath it, right? But I'm going to shift the n over to the other side, and I'm going to say it's 2n, and I called this n1, right? So I'm going to call this n1 times t. My acetone is n1. Okay, I'm labeling these sub 6s just because I want to denote it's that wavelength that I'm talking about. Not that there's 6 here and 6 plus a half. No, it's just that I'm talking about that wavelength. And that wavelength may have a different index number than the other one when I look at the construction of the 700. It may have a different index of how many wavelengths we're talking about. In fact, I'd be surprised if it didn't. So somehow you have to keep track of different m values, and this is the way I'm going to do it. You could call one m and one n. No, you couldn't call it n. That would be bad. You could call it p and q, or you can call it m1 and m2. I'm just choosing to call mine m6 and m7. We're going to look at the construction of lambda 7 here. So we'll have, in this case, m7 lambda 7. Okay, m7 lambda 7. This is going to be constructive because remember, an integer number of wavelengths is going to cause construction because I have no extra phase shift due to the reflection. So I have nothing that's out of bounds or nothing that's out of phase. When I say that, I can say for sure that if they constructed due to integer wavelengths here, then they're going to continue to construct because the reflection phase shift doesn't do anything. And this also is going to be 2n1 times thickness, like so. So the issue here is that we don't know the thickness, and we also don't know these m values, okay? So what I'm going to do, I think perhaps the easiest case here is to pick a couple of m values and solve for some thicknesses that would have created that m value, and then do the same thing for the next one and see where they overlap. So let's give that a try. I'm just going to do that down here where I have glass, but I'm going to erase the glass, and we'll just do it right here. All right, so if I solve the top one here for thickness, right, I'm going to say, okay, that thickness is equal to, I'm going to swing the 2n underneath the lambda. I'm going to get m6 plus 1/2 times lambda 6 divided by 2n1. Okay, like that. And so, let me write that a little bigger. Sorry, I'm getting a little cramped here. And so what I'm going to do is just choose a couple of m values. I'm going to choose a couple of m values in order to try and figure out, okay, well, what would be the thickness here? All right. So if I start with m6 of being 0, that would mean it's the first destructive interference, because the path length difference and the wavelength reduction have combined to give a half wavelength difference between the phases of the waves as they come out. I remember I'm gaining nothing by the reflection phase shifts, so those are basically out of the picture. And so what I'm going to find is I'm going to get lambda 6 divided by 4n1. Okay, so n1 being 1.25, I know that 2n1 is going to be 2.5, therefore 4n1 is going to be 5. And this is basically 600 divided by 5. So 600 divided by 5 is 120. So the thickness, the smallest possible thickness at which I destroy the 600 nanometer light is a thickness of 120 nanometers, which is a fairly small thickness. But if you think about acetone, that's a fairly complex molecule that's got, I think it's got multiple things in it, like hydrogens and carbons and things like that. So the size of that molecule might be about a nanometer, say. Atoms are typically, if you think about hydrogen, it's about half, or say it's about a 20th of a nanometer in size, is the size of a hydrogen atom. So saying that a molecule is about a nanometer in size, well, that's rough, but nonetheless. So this is about 120 atoms thick of a layer. And so that's by no means out of the realm of possibility here. That's absolutely something that could happen. If I take a look at, this is for M6 being 0. So if I look at M6 being 1, maybe I should make a table here. That's what I should probably do. I should go, this is for M6 equals 0. All right, so for M6 equaling 1, I'm going to get 1 plus a half, which is 3 halves. And so I'll get the same half down here, but now I'm going to multiply by 3, so that's 360 is the second one here. That would be the next thickness that would cause destructive interference. Let's look at the next one. If that's 2, 2 plus a half is 5 halves, so I can take my 120 and multiply by 5. So that looks like it's going to be the 600. All right, and if I do, say, a third one, so that's 1 full wavelength now. But no, well, 1 full wavelength in air, but notice, of course, the wavelength is reduced in here, so that's what's causing the destruction. If I go to M6 being 3, I'm going to get 3 plus 1 half, which is 7 halves. So I'm going to have that being multiplied by 7, which is 840. Okay. So I'm just creating a table of these are the thicknesses that would cause destructive interference for the 600 nanometer wavelength. Okay, what about the construction of the 700 nanometer wavelength? If I do the same basic thing here, and I say, okay, well, I'm going to take the construction here, solve for t. I'm going to get M7. Actually, I'm going to make that by itself. I'm going to do the same thing. I'm going to have M7 times lambda 7 divided by 2n1. Like that. So I still have lambda 7, which is 700, and 2n1, which is 2.5. Excuse me. Okay. So I'm going to have the 700 divided by 2.5, and now I just have to pick M7 values, and I'm going to do the same thing. I'm going to say, oh, what if I choose 0, 1, 2, 3? At the point when I find a thickness that overlaps one of these, that's the thickness that does both. Okay. So I'm probably going to have to go over here. We'll do M7. Obviously, the thickness would be 0 if M7 was equal to 0. That would be like the constructive central bright fringe, right? There's basically no path length difference here, and therefore it comes out very bright. If I have M7 equal to 1, then I've got 700 divided by 2.5, and 700 divided by 2.5. What is that? I wrote that down. It's 280. M7 equal to 1. All right, let's look at M7 equal to 2. That's going to be, that's a 2, which then cancels with this 2, and I've got basically 700 over 1.25, which is the same as twice that much, which should be 560. If I do M7 equal to 3, I'm going to get this same number here multiplied by 3, so that's going to be 740. 7, wait a minute, if I do this by 3, it's going to be 602, no, it's going to be 840. 840. Ah, excellent. 840. Okay, so yeah, they do overlap right on the 3. Good thing I stopped there. That is the lowest thickness that causes both things, right? If I go another one, I'm going to find 4 times this much, which is going to be some 1200 some odd. If I do a number 4 here, that's going to be, I mean, you can see how it's going to go. But the point here is that this one is the one that solves both of the cases that we're interested in. All right. Okay. Now, one other thing you can do, okay, and you're probably saying, well, why am I doing all of this? Why am I doing all this kind of trial and error here? Wouldn't it be possible to take these two things? They're both equal to 2n1 times t. Why can't I just set the left-hand sides equal to one another? You can. You can certainly do that. That's absolutely valid. You can do m6 plus a half times lambda 6 equal to m7 times lambda 7, where I know that the wavelengths are 700 nanometers or 600 nanometers. So if I want to say what's the relationship of the m values, I could just divide these over by each other and say m6 plus a half divided by m7 is the same as the ratio of lambda 7 to lambda 6, which is the same as 7 divided by 6. So from that, does it make sense that both of these are 3? Because this is 3.5 over 3, and that's the same ratio as 7 over 6, right? So from that perspective, you could do the same thing. Okay. All right. So you can table them out like this, or you can try solving. One or the other will work. One of the main takeaways here is that you have to account for all 3 interferences. And how you do that is kind of up to you. It's a little bit of a learning process. I have my way of doing it, which may or may not appeal to you, wherein I set myself in the mentality that I'm going to assume that the double slit conditions apply. And then I'm going to say, I'm going to look at the reflection phase shifts right away
because when I look at the reflection phase shifts, I know if that's true or not. In other words, I know whether or not the double slit conditions actually apply or not. Because if I look at the if I look at the two phase shifts from the reflection and I say, look, they're both the same, then yeah, double slit interference occurs. I'm sorry, not occurs, but it's valid. The conditions are valid. In other words, your path length difference, even though it's in a reduced wavelength format, if that's equal to in an integer number of wavelengths, that will result in construction. Integer plus a half means destruction. Okay. Now, if I look at the reflection phase shifts and I go, oh, I've got a difference here. I've got one at pi and one at 0. Well, now I know those are not going to quite work. I have to flip them. Now I need to throw in the extra half wavelength in order to get these things back in phase if I want construction. And that means that m plus a half, when these things are unequal, when these things are one's pi and one's 0, when I look at those phase shifts and I go, okay, I need that extra half wavelength, now it's m plus a half, that gives me construction. Regular, if I just leave them as they are, pi and 0, that's going to tend to destroy if I have an integer number of wavelengths in the path length difference down here, plus the wavelength reduction. So trying to explain how I think of it is possibly helpful and possibly not. So point here is that you don't always have to make this huge chart, right? You don't always have to do all of these things all at once. I'm just trying to show you, here's a particular situation. We'll do another situation here in just a minute, but hopefully that gets us off on the right foot. And like I said, you can come up with your own mentality of how to do things. I try, because the double slit is so simple, I try to start thinking in that mentality and then say, if this is happening, that's an okay mentality. If this is not happening, I got to change and go to the other. I got to change the destruction and construction over, basically. All right. All right. So hopefully that makes sense. Let's do another example here where I'm going to do a slightly more, I'm going to take a slightly more complicated shape, and we're going to look at the interference of it. And this is, and I'll show you this. This is once again one of those things I'm not sure you're going to be able to see, but maybe, maybe, let's see here. So if you look, at this thing, and I'm trying to get a bit of glare off it and see if you can see what I see. Now, where are we looking here? Okay. That's too much, so let me back that off a little. Okay, now, oops, right there. So can you see the dark spot in the middle right there? Right there, there's a dark spot. And I'm not sure if you can see, there's kind of a white ring around it. Oops, hold on. Right there, there's kind of a white ring around it. And maybe or maybe not you can see, but there's another succession of dark circles. So I'm getting interference in here. And I would like to be able to show it to you, but I just don't know if it's going to, if I can have it. Oh, there we go. If I hold it, here you go. I'll get it really close. Maybe you can see this. If I go, ooh, I saw it really, there you go. There's a dark spot, there's a bright ring, and then there's another dark ring, and then there's another bright ring. That's all, whoops, I'm messing it up here. That's about all you can see, I think. Anyways, when you look at it from this, when I look at it, there are, I'm not even sure I would venture a count here. but I'm going to say there's probably about 100 circles that I can see, bright, dark fringes. And that is because what we've done here is we have two thick pieces of glass that are screwed together, that are being held together by these black plastic rings. The two pieces of glass are being held together, but there's a little tiny thing in there that's causing a small. There's a thing in there that's causing a small gap in between the two glass plates, and that's what's causing the interference here. These are known as Newton's rings, and yes, it's the same Newton. Let's see here. I think I am getting told that I need to plug this thing in, so let me do that. Maybe that works. All right. Okay. So I want to look at something that's similar to that, and try to see if we can't do an analysis of this. So let's look at the interference here. I'm going to take a rather oddly shaped thing here, and I'm going to bounce light off it. And as always, it's going to be normally incident. So what I'm going to do is I'm going to look at the interference pattern that's developed here. All right, so I'm going to go like this, and over here maybe I'll go like this, like so. All right, so I'm going to have this wedge-shaped thing here. All right. Actually, you know what? I think I'm going to flip it over so we can have incident light be the other way. All right, let's do it that way. Let's do this. Unhappiness with that. Let's do this instead. Let's make it so it's. I just told you normal incidence, so let me just stick with normal incidence, and then we'll go like this. There, that's better. All right, so we're going to do this, and we're going to say, all right, I've got normal incident light coming in here. Okay, so there's my incident light. And what am I noticing? So I'm noticing that the interference pattern, okay, is formed by what? Well, I've got a bounce off from the air glass surface, and then some of it's going to go into this is, by the way, a piece of glass. So let's just say we've got a 1.5 piece of glass here. Right, so I've got a bounce off from the reflection on the top surface. It goes through, bounces off, comes off, and those two reflection waves are interfering. Same thing's happening over here. I get a bounce off the top surface. Nothing's different from that situation than it is from over here. But now when I think about how much more it's going through here and coming back out and bouncing off this big, right, longer, it's traveling more wavelengths, got a longer path length difference, in addition to which the wavelength is reduced. Okay, so what we're going to have out here is air, n equals 1 out here, n equals 1 out here, and so we're going to look at the phase shifts of this situation. And I'm going to say that we have incident light, and let's suppose our incident light, I'm going to make this a particular wavelength. So let's say incident wavelength is equal to 630 nanometers. Okay. Okay, so let's assume that this glass is surrounded by air, and it's or however it's held up in air, and I'm looking down here, right? I'm looking from the top at the reflected beams and their interferences, and I'm seeing 10 bright fringes and 9 dark fringes. In other words, if I tried to sketch what the top of this looks like, let's try and do that down here, top view.
if I tried to sketch what this looks like, and make this nice and big. What will work? A bright spot. I've got red being the incident light. So let's make, when I draw a red thing down here, then that's a bright spot. And when I draw a black one, that's a dark spot. Okay. So what I'm going to notice then is if I have 10 bright spots and 9 dark spots, that means I have one less dark fringe than I do bright fringes, which means I have to have bright fringes on either end. And then I've got 9 dark fringes in between those. So I'm going to have a bright fringe here and a bright fringe here. And I'm going to have dark fringes in between these two things. Like so. And there's a succession of 10 of these. Now, I'm not sure I'm going to get the spacing quite right, but I'll give it a try. I need to draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'm going to try it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Oh, wow. I got it. I did real well. Okay, now they're separated by dark fringes. So 1 dark fringe, 2, 3, 4. I'm just going to actually, you know what? I'm not going to do it that way. I'm just going to give them like this. Okay, that's 1, 2, 3, 4, 5, 6, 7, 8, and 9. All right. Okay, so the interference pattern looks something like this. It's kind of busy, sorry. But it's got 10 bright fringes and 9 dark fringes. All right, so what I'm interested in knowing is kind of what shape object do we have here? There's going to be some thickness over here and some extra thickness over here. So that's that thickness plus that thickness. The question is, how much extra thickness do we have? How much thicker is this side? Okay, that's the question we want to try and answer. Okay. So, if we know that we've got 10 bright fringes, then I'm going to go ahead and write, because we have bright fringes on either side, I'm going to call this distance here, I'm going to call this L1, and I'm going to call the entire distance here L2. The entire distance. And then basically what I'm looking for then is L2 minus L1. Which I'll just call delta L, something like that. Okay. If I set up now the conditions for interference, for constructive interference, what do we have here? Okay. Well, what we're going to do is when this thing hits here and bounces off, I'm going to get an R1 from the top. I'm going to get an R2 coming out here, like that.
since this thing is surrounded by air, notice I'm going to have a difference in the phase shifts. My R1 is lower index to higher index, so R1 comes out as plus pi. But my R2 is going from glass into air, which is higher index to lower index. It does not phase shift. So there's a plus 0 on that. Okay? That means that when I think about these two waves causing a bright fringe, I have to chuck in an extra half wavelength in the path length difference plus the wavelength reduction in order to get these two things back in phase so that they're swimming to make constructive interference. Okay? So for a bright fringe, I'm going to take that extra half wavelength that I need to put in there, and I'm going to say I need to do, I'll call this M1 plus a half times the lambda naught that we know, and the lambda naught here, lambda naught is 630. That's you're always given wavelengths in air. Nobody knows what the wavelengths are in water off the top of their heads, right? It's always the wavelengths in air. So I'm going to have m plus a half times lambda naught being equal to 2n, and in this case, it's going to be L1. That's the thickness of the glass over there. Okay. So this is bright fringe number 1. Number 1, that's 2, 3, 4, dot, 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 dot. This is 10 over here. Okay, so if I write for bright fringe number 1, I get that. If I write for bright fringe number 10, I'm going to get basically the same thing, but the M value, the M is going to change. Also, the L1 changes to L2 because now I'm over here on this edge, and that means I'm getting a longer distance in the glass. All right, so bright fringe, this is bright fringe number 1, and this is bright fringe number 10. I'm going to get M10 plus a half times lambda naught equal to 2n times L2. Okay. Hopefully good so far. I'm going to now check in and remember what I'm looking for. Really what I want to look for is L2 minus L1. So if I kind of subtract those two things, I'll be able to manufacture this quantity. Okay, so let's go ahead and do that, because otherwise I'm just wasting time. Well, I'm looking for other things? No, I'm looking for that. So I can make that from this set right here. A couple of important things before we go into algebra land here. Please be sure that you're understanding why the m plus a half is here. Okay, please be sure you're understanding why the m plus a half is here, and it's down to these two phase shifts. Okay, my mentality is, oh, they're going to construct, it's going to be an integer number of wavelengths. Oh no, they're not. I need an extra half in order to make them construct. Okay, and that's what this is telling me. So now I have to go here if I want the bright fringe construction. Okay. Second thing, the index here is, I don't know what the index is, but I'm observing 10 bright fringes, which means this one's 9 more than that one. I don't know what these values are, but I'm going to subtract them. So when I look ahead as to what's going to happen when I subtract these two equations, I'm going to get that one minus that one. And I don't know what those are, but I do know that that one's 9 bigger than that one. So I'm going to subtract them, hopefully. It'll come out with 9. All right, so I'm going to find out that 2n times L2 minus L1. Right, if I just take this one and I'm going to multiply the top by a negative and add, right, or whatever. So if I factor this out here, that's what the side over here looks like. Now I'm going to get this side over here, which means I'm going to get M10 minus M1. And of course, the halves are going to go away. I'm going to get a lambda naught out here, and I'm going to realize kind of what I was talking about, which is that this one is 9 bigger than that one. Okay, it's 10 bright fringes. So if this is number 2,814, well, this is number 2,824. All right. Okay, so I should be able to get 10 minus 1 here, and that should give me 9 lambda naughts. Therefore, my delta L is just 9 lambda naught divided by 2n. And that's going to be some number because we have numbers to put into it, but ultimately nobody cares because this is just a made up problem. However, the mode of solution is what's important here. Okay, so it's thinking about the reflection and the interference. It's thinking about all the ways you're getting the interference, right? Starting with assessing the reflection phase shifts, going to path length differences, seeing what you need in order to make brights and darks, thinking about the pattern of brights and darks, right? What does it look like? And then thinking about, okay, well, I'm going to have this many, and so when I get this difference formed up here, I'm going to get a difference in the m numbers. Okay, so this turns out to be some number which is probably relatively small because this is going to be what, 3 on the bottom, and that's already 9. So it's really like about 3 times this wavelength, which is great. Okay, wonderful. That's how much thicker the glass is on this side than it is on that side, which means someone was very precise with how they made this glass. And I like it when people take care with things. Okay, great. So anything else that I want to say about this? I don't think so. Just that when it comes to thin film interference, remember you have to take all 3 of the interference mechanisms and put them together to try and figure out how the interference is happening and what type of interference is therefore happening. Or in this case, we know what kind of interference is happening, so how do we get to that? All right. Okay. I think that's probably reasonably good enough for the thin film situation. I know I gave you a couple of problems, one on a reflection interference, and I got you 2 on some thin films, and those are pretty, they're, what would I say about those? They're not overly challenging unless you try to do the whole thing all at once. If you break it up into steps, the steps themselves are fairly simple. What's complicated about the problems is the chain of the set of simple steps. So try to think simple, okay? Try to think about one thing at a time. I'm assessing, right? I'm assessing the path length difference. How do I get that, okay? And certainly for those last problems on thin films and interference, a drawing is really going to help you out, okay? Especially with that one, well, the one where I have the curved glass on top of the other glass, really take a close look at a drawing there to see what's going on. For that one, I wouldn't do a lot of algebra after you've gotten an answer. Don't try to make that one pretty. It's not really going to end up great. For the one with the reflection phase shift off the water, I would suggest thinking about the law of reflection and using that to go along with figuring out what the path length difference between the reflected wave and the straight wave is going to be. And then when you're done with that, add on the extra reflection phase shift, the extra half wavelength for the reflection phase shift. And then you'll come out with a condition for the difference of the heights, I think it is, of those towers. Okay. Trying to do it all at once, trying to think about how do I get all the way to the end. Don't try to think about getting all the way to the end. Try to think about how do I get to the next piece. And then when the next piece arrives, how do I assess that? Okay. So kind of like this, how much thicker is one side than another? Okay, I've identified what I need to do. How do I get there? I'm not getting directly there, right? I'm thinking about, okay, what do I have here? I got to write out constructive conditions for the two sides. Okay, now I got to think about, oh, I can form this up by doing a difference here, right? There are steps in between just going straight to the answer, all right? And a picture will always help you there. Okay. So, with that being said, we are leaving interference between two waves. And we're going to go to interference of more than two waves. Oops. Okay. Now, I don't know whether or not you've noticed, and I didn't bring in specifically, a two slit, but let me see if I have, yes I do. Okay. Okay, I showed you these things before, remember? My cool glasses, oops, it's not gonna work, and my laser. So, oh wow. Oh, I'm getting pretty good. Can you see that? No, I don't think you can see that. That just looks like the sun. Okay, I'm actually getting really nice ring. I'm getting a set of rings around the bright spot here, which is pretty cool. Unfortunate that you can't see that. Anyways, I showed you this before where I put the glasses in the way. Whoops, I put the glasses in the way. And the bright there is still the bright spot, right? That's like a central maximum. But what's going on with all the rest of this stuff? Okay, what's going on with all the rest of this stuff? So these things don't look, if you look at them carefully, they don't look, right? You can see through them. They are transparent, right? So what's going on? It's a situation where I can see into and through these, but when I shine light through them, they seem to do some strange things. Okay. And it's not just a two-slit setup. It's not, that's, if it were just a two-slit setup, they would be much darker. You wouldn't be able to see through them, right? So what I want to do now is start thinking about, okay, if I'm looking at light going through slits, we've looked at light going through two slits. What happens when, and this sounds funny, what happens when we look at light going through one slit? It turns out that this is much more difficult. I'll show you why. In the sense of naming, I don't know why this name happens, but I will tell you this. This two-slit interference happens to be called interference because we can easily conceptualize, I have only two waves and they're wiggling and they're meeting here, and I'm assessing how are they meeting? Are they meeting such that this one's at a peak and that one's at a peak, or that one's at a peak and that one's at a trough? So we only had two waves to deal with in the two-slit interference because we had the situation where we could make the slits thin enough where they, in our minds, we could model them as only allowing one wave of light through each, right? So I had one wave coming through this slit, one wave coming through this slit, and that's how I was drawing it. But that's not really true, is it? We can't really make only one wave come out of a slit. That doesn't really work. So we have to think about what happens when a lot of waves come out of a slit, because that's really more the situation. Okay? So we're going to talk about single slit interference, which does not go by the name interference. And so this is the first hurdle to this, at least for me, naming and understanding words to me is important. Maybe it's just me, but this is really what we're talking about. We're still talking about interference in the sense that if we have waves that hit and they're all at a crest or they're all at a trough, then we call that constructive interference. And if we have this situation going on, that's still destructive interference. But because we're going from two waves in the two-slit interference to many waves, this now goes by the name of diffraction. Okay. This is equal to diffraction. All right, so that's the first thing to realize. I'm going to start talking about diffraction, and you go, what's that? That's totally different. No, it's the same thing. It's really the same exact thing as interference. It's just that we have to deal with a lot more waves. All right. So in the sense of what is diffraction and how do we do this? All right, so let's take a look at a single slit. And I'm going to do the same thing. I'm going to have a laser back here, and it's going to have coherent waves coming out, and it's going to hit a single slit, and I've got a screen on the other end. The setup is identical, right? It's just that now I have one slit instead of two. Okay, so here's my single slit. And we'll put a screen over here. And we're going to think about what happens when we shine light from over here that way through the slit. And you'd say, well, that's like, what are we doing here? What, really? It's just going to make a shadow, right? There's light coming through. The light's just going to be right in here, and then everything else is going to be in shadow, right? And what if I make the slit narrower? Light has this very funny property where when you try to confine it and you say, I want fewer rays, right? If you go back to the ray optics model, I want fewer rays of light coming out of here, fewer beams. I want to get down to maybe a couple of beams, maybe even one beam of light. I can just narrow this thing down until there's only one beam of light coming through here. But this is where light acts out, right? When you squeeze the light to try and make it go through a smaller and smaller and smaller opening, what you find on the screen is that it doesn't hit in a smaller and smaller and smaller pattern. It hits in a bigger pattern. It's as if you take this thing here and it spreads out, right? As you narrow this down, you get a lot more spreading. And that is hard to deal with, okay? Mentally, that's hard to deal with. But first, let's start by taking a look at, say, 3 or 4 waves coming out of the slit, okay? Suppose that we just, this is only, I'm drawing this. Really, there's an infinity coming out, but when I'm just drawing 3 or 4. Suppose that I've got coming through here 1, 2, 3, 4, like so. All right, and they're coming through, and I'm going to ask, okay, what kind of pattern are we going to get on the screen? Okay, well, can you think about this as a set of 2 slit interference patterns? You kind of can, right? Because if I think of the waves, now I'm going to be kind of careful here. I'm going to be careful. I'm going to think of the wave at the outside, right? This one that's way out here. And I'm going to think about how does that one interfere with the one that's down here. And then I'm going to think about the one that's on the other side of the slit. It's way over here. As interfering with the one that's over here. Like that. And I don't know if you can see the difference in the colors, but hopefully you saw the pattern that I was drawing. If I considered just pairwise, right, like nearest neighbors, I don't know, it feels nicer to do it this way, where I can just say those 2 are the same and those 2 are the same. I'm going to overlay those 2 patterns. Since I can think of this as a double slit experiment twice, these two sets of two waves are going to come straight through, and they're going to hit the central maximum here with zero path length difference. So if the same thing about the double slit is still true in the single slit, which is light going straight through suffers zero path length difference and therefore constructively interferes here, this should be a bright spot. And that kind of hopefully should make sense that between here and here is a bright spot. This is still the bright central maximum. Okay, this is still the bright central maximum. Okay, now I'm going to start thinking about these sets of two waves going up at an angle. I always choose up. I mean, I could choose down. It doesn't really matter, whatever. But I'm going to choose them going up at an angle, and I'm going to ask, okay, what's the path length difference now? Okay, well, I'm going to say, well, if I go up here and I'm going up at some angle, then I can draw the same type of triangle as I did before, where if I have one up here going like that, and one down all the way down here going like that, there's a path length difference between the two waves that are at the very edge of the slit, right? And that path length difference I can still find in exactly the same way as I found the double slit path length difference. If I just take this situation and blow it up and I put it down here, so here's one right there, and I'm going to say here's one right here. Okay, so this is the edge of the slit, and this is the edge of the slit. Okay, and same type of geometric reasoning. We're going to say this one's going up at some angle. This one's going up at that same angle. In other words, they're parallel, but they will intersect when they hit the screen because the angles are small. So I can take this here and I can find the path length difference by making a right angle here, dropping a normal down onto this lower ray, and saying my triangle looks like this, all the way the entire width of the slit, all the way up here, and then all the way through here, all right, like that. Okay, that can be a path length difference between the outermost rays. Okay. Okay. The question you might have, though, is how do we consider the set of bright fringes and dark fringes that we see in a single slit pattern? And so how much time do I have left? I may be just about running out of time here. So if I said to you, well, I want these two rays to cancel, these two waves to cancel each other out. I want destructive interference, okay? And I want to be able to get destructive interference between these two. Okay, so if that's going to happen, that means the path length difference is a half a wavelength, right? But what happens now if I go to some of the inner rays? What if I look at the two rays that were in here? Well, that path length difference is not going to be a half wavelength, right? If I said these two waves are going to destroy each other, then the path length difference is a half wavelength. Okay, what are these two in here going to do now? Because remember, I drew four waves here. So I have two at the slit edges, and I have two in the middle. Well, these two are not out of phase with one another because the path length difference is not a half wavelength. It's just the distance is too short to fit a half wavelength in. Therefore, if I say, oh, these two cancel, well, these two don't, and I get some brightness on the screen. Now, it's not full constructive brightness, but it's partial brightness, okay? So what I have to do now is think about, okay, well, what if I want total destructive interference, then what I really should do is think about what happens to the ray right in the middle, right? The ray right in the middle here, and the ray right in the middle here. And I think about pairwise cancellation. If I take the ray on the very edge of the slit and I take the ray that's right just before the center of the screen, sorry, the center of the slit, and I say those are going to cancel each other. Okay, now what I can do is I can say, okay, now I'm going to move to the next wave here, and that means I move to the next wave here, and 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 the next wave here. Oh, look, I can pairwise cancel every one of them, okay, if I have the right path length difference at the right angle. So the reason that single slit diffraction, right, the reason that the interference has gotten so much more complicated is because we have to now think of how do we break up all the waves that are coming through the slit into a situation that tells us what kind of interference we have on the screen. Is it a bright spot or a dark spot or a slightly bright spot, right? That is more, I would say, I guess, more bookkeeping. Okay, so it really is interference because the waves are still interfering. There's just a lot more of the waves that we have to keep track of, and that's been called diffraction for some reason, and I'm not entirely aware why, but that's the situation. When you get multiple wave interferences, it's known as diffraction. Okay, but I'm going to stop here because I think that's probably enough time for today. We will pick up with talking about single slit in bright and dark spots. And then, just to give you a preview, I want to then go back to the two-slit interference pattern because the two-slit interference pattern showed some of the single-slit pattern as well. And we didn't address that. If you've been looking carefully at two-slit patterns, you will have noticed that there's kind of an interference pattern that looks like Dr. Teeth, and then there's then there's kind of another one that's going on. There's like a bright thing here where all these bright and darks are happening, and then all of a sudden there's a dark thing here, and then there's another set of brights and darks here, and then there's a dark spot, right? That is due to the single slit effect. But more about that probably not tomorrow, but probably Thursday, and we'll go from there. In the meantime, I'll say happy day to you folks. I hear some rain is coming here on the Central Coast, though the sun is out right now, and it looks promising, but apparently we're going to get a bit of rain. Hopefully not too much, and hopefully not massive gusts of wind, and we'll be back to Central Coast living soon enough. And I wish you happy rest of your day. Do please be sure to work on homework 2, get it all set to turn in, and be ready to take quiz 2 on Thursday. Alrighty? Have a great rest of your day, folks. I'll see you next time.